Okay, Jackson, so you're trying to turn an acetic acid into an ethyl ethanoate. So what that is, an acetic acid is going to be this structure right here. It's also known as a ethanoic acid, so because you have an ethyl group and then you have a carboxylic acid. So you have two carbons, one here and one here, and then you have a carboxylic acid. So this is what is known as acetic acid, or its IUPAC name, which is ethanoic acid. And then we're trying to convert that into ethyl ethanoate, which this here is a carboxylic acid, is the double bond O, and then the OH signifies this is a carboxylic acid. This ethanoate, this naming is the IUPAC naming that signifies that it is an ester. And so ethyl, so this ethyl part here is the same part as this etha right here, meaning this and this, and then this etha signifies that the ester has a ethyl group on the far side of the oxygen. So we draw an ethyl, and then we have an oxygen here like before, and then this double bond oxygen like before, but this is an ester, which means attached to this O, there's an ethyl group like this, which this can also be written like this. So now the question is, how do we get from here to here? So the simplest method is going to be what's called a Fischer Esterfication. Because we're esterifying the carboxylic acid into an ester. And so how you go about that is you just add an ROH in an acidic solution. So here, this R signifies an alkyl group that we want to add. And since we have 2 carbons here, and then 1, 2, 3, 4 here, specifically this one, 1, 2, that R group is going to be 2 carbons, which is the ethyl group. So then the products are going to be, this is going to be an ETOH added with acid, and then that'll get you the Fischer Esterfication that yields an ethyl ethanoate. So you might recognize this ETOH as also ethanol. So generally what this means, or how it's going to be said is written on words, is that acetic acid plus ethanol and acid yields ethyl ethanoate. Now, this is Fischer Esterfication is what we call a PNP-PLP reaction. So first is a proton transfer. So we take the like this, and then probably be best to write it like this. So the mechanism is as follows, where you have the ethanol attached to the oxygen, and then you have this hydrogen here. So you have to remember that this oxygen right here is going to, since it is double bonded, it's going to have 2 lone pairs, and so then it attacks that H. Then these electrons that are bonded between the H and the O are going to go back into the O to form the following compound. This is the P, or the proton transfer of this, which now that forms, and since this is an acidic solution, technically speaking, this should be like a double H here. And so now this is a oxygen with a hydrogen on it, has a lone pair still, but this is still a carboxylic acid derivative. But because of this new added proton here, this is now a positive charge. So the next step is you're going to have a nucleophilic attack, which is the N as indicated up here, where the oxygen from the ethanol is going to use its electrons, or one lone pair of electrons, to attack this carbon right here, this carbonyl carbon, and with that, it's going to then push this double bond back up into the oxygen, removing a pi bond and putting back up into a lone pair. And so then that is what was known as a nucleophilic attack. So then you have that. So this oxygen is now back to an OH with two double bonds, or two lone pairs rather. And then you still have this group is the same as before, which this here is just a methyl, this part right here. Then this is your OH still from here, but now you have an O with an ET and an H bonded on like that. So the next step is a P, which is another proton transfer. And what that looks like is that your ethanol is going to act like a base. So another ethanol is just going to act like a base, and it is just going to come and steal that hydrogen. The electrons are going to go back up into this oxygen, and then so this will form a ethanol with an extra proton. However, now this results in this being transformed into this molecule here, where you have two OHs and an OET. And then technically speaking here, this oxygen is positive, but now it loses a proton and gains that, so now it's a neutral oxygen now. So then once more, you're going to do another proton transfer, the next P. So what this looks like is that another proton transfer. What this is going to look like is that you are going to take just your acid in general. So in this case, we're using H3O+, which is just a hydronium ion, which looks something along the lines of this. Now you see, it's just going to kind of go up to this OH right here. Or excuse me, the other way around. The lone pairs of this OH, or of this O, of this oxygen, are going to come and they're going to attack and just kind of grab away this H. Protons are going to go back in here, and so then that here just turns this into water. But then this proton transfer gives you methyl group there, an oxygen with an ETOH still, and then now you have this OH2 kind of group right here, which is just kind of like a water. So then this is what is known as water. Is a great leaving group. It wants to kind of be on its own, because like water likes to be by itself, like how you see in nature. So then PNPPLL, which is a leaving group. And so what happens basically is you have these electrons on this oxygen here. They're gonna just come back, form another pi bond, which is a sigma bond, and then the pi bond, which is a second bond. And now this carbon's overloaded, so then it just chooses to electively kick out this OH, and then you're left with a OH double bonded to a carbon with an OET on it. Now this is still a positive charge now, because you have 1, 2, 3, 4, 5 things on the carbon, on an oxygen. So then you need one more, the proton transfer, where you take your ethyl or your ethanol, and it is going to once again come steal that, push these electrons back into the oxygen, and so then you end up with just a double bond here and a neutral oxygen. And so then that is how you form ethyl ethanoate, which is what we did up here. Okay, Jackson, I think you got that. Good luck.